So I will start after at 10 o'clock exactly, but now since I am here, since some of you may be there, if there is any student who wants to ask a question now, I will try to answer them before starting my lecture. In the last week's lectures, if there are any questions or doubts, please ask. Yeah. Yeah. Is it? Okay, I will tell you. I gave the reason, but I will explain it again. See, it comes as a resonance between the two particles only because its mass is higher than the total mass of those two particles. So it has to decay, and it decays by strong interactions. Since it decays by strong interactions, it lives only for 10 power minus 21 seconds. So it cannot leave a track, and so it manifests itself as a resonance. Now I will give you, I gave the example of last time neutron and deuteron. Deuteron, which is the nucleus of the deuterium atom, consists of neutron and proton, and because of the binding energy, the deuteron cannot decay. Deuteron is stable, it is a stable particle if you like. But neutron, since it is heavier than proton, it decays. So neutron decays, deuteron is stable. Does it mean that deuteron is a particle and neutron should not be regarded as a particle because it decays? That is not true. We know that neutron is a fundamental particle. I mean, it's more elementary than deuteron because deuteron is made up of neutron and proton. So you can see that there are many hadrons which happen to be much heavier than nucleon and pion and so on, nucleon plus pion and so on. So they have to decay by strong interaction. Since strong interaction does not forbid them, and there is enough energy, mass difference converted into energy, so it decays, that's all. So this is a very important point in hadronic physics, that any resonance also is an equal hadron to the proton or pion or anything like that. Am I making myself clear? Yes. Yeah. So we discussed the delta resonance last time, which the mass 1234 or something like that, and that is higher than the total mass of the nucleon, which is 940 plus pion mass 140. So delta can decay into n and pi, and so it does not live long, it cannot leave a track, it can be seen only as a resonance when you collide pion, when you make pions collide on a proton target, then at a particular energy, namely when the center mass energies of these two particles is equal to that mass of that particle 1234, there is a peak, Breit-Wegner resonance. So that is how many of the hadrons were identified. The hadrons which I have discussed so far is only a minority. Majority of them, which I am going to talk about now soon after 5 minutes, they are all resonances. But resonances and the stable particles both are have equal right to be called hadrons. That is the point. Yeah, any other question?
we have something called the virtual process, right, where the particles are created.
Yeah.
Within a lifetime, very small lifetime.
Yeah.
But this resonance is different from that virtual process.
No, virtual particles come as intermediate states in perturbative quantum mechanics or perturbative quantum field theory. Okay. So that is not the same as resonance. For instance, this simple diagram which I have talked about already in quantum electrodynamics, electron exchanges a photon with, let us say, proton. This is what leads to electromagnetic interaction. In this photon is a virtual particle. But this is not a resonance. Virtual particles will always come as intermediate states, neither as initial states or final states, and they play a very important role. Actually, virtual states come even in ordinary quantum mechanics. We don't have to go to quantum field theory, but in quantum field theory they are very important. What is the difference between virtual particle and real particle? For real particle, electron for instance, its mass me squared, as you know, is equal to energy squared minus p vector squared. I am putting c equal to 1 always, otherwise it is confused. So, if you take the energy and momentum and take the difference of their squares, it will be always rest mass squared. So, this is real particle, and for virtual particle, mass squared is not equal to energy. That is the important thing, and that is what happens in quantum field, relativistic quantum field theory. But in ordinary non-relativistic quantum mechanics, you might know that virtual particles in the virtual states, energy is not conserved. But relativistic quantum field theory is fully covariant, and hence energy alone cannot be picked out. So, in the formalism, it is the mass which is not equal to E squared minus P squared. Okay. So, that is the difference between virtual particle and real particle. For instance, for photon, this photon, for photon of course, we have if you define m squared is equal to energy is the same as frequency, remember, putting h cross is equal to 1, and its momentum by de Broglie's relation or Compton relation, you can write this. But for this, and m squared has to be equal to 0 for real photon. Remember, photon has 0 mass, so it is 0. But for virtual photon, for this photon, this will not be true. One can write down some virtual electron also. Let us try to write down. You can easily see what this process I am talking about now. These are all quantum electrodynamics, which it's better to learn before coming to particle physics. But anyway, I will give some introduction to quantum field theory as I proceed. Electron collides with photon and becomes a virtual electron and final photon. These particles are all real, and so they will be on the mass shell. This is called the mass shell condition. Again, I am tending to write small mass shell. For this E, energy squared minus p vector squared is not equal to me squared. So, it is virtual. So, virtual states will come in all the Feynman diagrams. Okay? Yeah. So, shall I start now my lectures?
Yeah, just before starting.
Yeah.
Right now, whatever we have written
Yeah.
is very small.
Yeah, now today I will try to write in very big letters, and warn me, as soon as I tend to become small, I will keep remembering, but you please warn me, prevent me from going further. Okay? I don't mind. Yeah, I don't mind the interruptions of any kind. Okay?
Now, if there is a possibility from the camera side?
Yeah, I don't know. Can I ask Kripa?
Yeah, I'm doing it.
Is it possible to zoom so that the letters become bigger? Because otherwise the blackboard will not be enough.
Okay.
Yeah, he will try to do. He will do that now today.
So the another one thing that the YouTube channel person
Yeah.
can name the lectures 3 and 4. Today is 3 and 4 lectures 3 and lectures.
Yeah, correct.
Put the title in the YouTube title. So that
Title கொடுக்கிறது கஷ்டம் because it is a continuous narration. So just say lecture 3 and lecture 4. That should be enough.
yeah, that I think the person is
There will be titles like resonances, and I will talk about SU2 symmetry, SU3 symmetry. Whenever those topics come, I will give the title. But you cannot start a lecture with a title because sometimes it is a continuation. For instance, resonances I started talking about in the lecture 2, and this will be a continuation. Okay. So I will simply say lecture 3 now, and at 11 o'clock it will be lecture 4. I think I should use only 2 parts of the board. Lecture 3. Is this visible now? Okay. So I will keep that as a model. I will not lower the size. So shall I start now? So as I already mentioned, I already talked about resonances. Last time. The first resonance which was discovered is called delta 1234, and this is the way resonances are written. This is the mass of the resonance. I mean the energy at which the peak comes, and that is really the mass. That is the first resonance to be discovered. But now I am going to talk about more resonances. Literally, there was a deluge of resonances. Hundreds of resonances were discovered. And I am not going to talk about all of them. I will give you a partial list. And please go to this particle data group, publishes every year PDG. You can go to the internet, Google or something, and get the complete book. It is there available. So all the particle properties, not only resonances, weak interaction, strong interaction, electromagnetic interaction, gauge theory, all the current information on experimental information supported by theory. There are small theoretical essays also. So it's actually a very good information for particle physics. You can go there and try to pick out any number and see what is the meaning of that number, how it was experimentally determined. You will learn quite a lot of particle physics. So I will advise the students to go to internet and find PDG, particle data group. So complete details of all the particles there. Okay, so let me start listing it's a partial list only. As I already said, there is no difference between nucleon and delta as far as the status of particles are concerned. So hundreds of hadrons were discovered, many of them in the form of resonances, and so I will not use the word resonance. It is simply particles, hadronic list. So hadrons, you remember, we divided into 2 categories, baryons. So let me start with the bottom here, lowest mass, which is 940 MeV, nucleon. All the masses are generally in MeV unless I specify it separately. So here I will open out the column. Mass is already given. So spin, parity, internal spin, and isospin. And these are all non-strange baryons. So let us say now, strange baryons I will separate. N. Then the next one is 1232 actually. I mean, it is very difficult to define exactly where the peak is because it is a very broad resonance. Remember, the width itself is 100 MeV. Actually, I should give width also here. Width here is 0 almost. I mean, there is a weak interaction neutron width, but it is very, very tiny. Delta. This is of course half plus. Isospin also half. This is 3 by 2 plus. Okay, my letters are becoming small. 3 by 2 plus, and isospin also 3 by 2. Anything which has isospin half is called nucleon. Non-strange isospin half object by definition is called nucleon, N, and the distinction is only through its mass. So, this is also called nucleon. So, you can say higher excited state of nucleon. One way to regard them is this is a ground state of a particle and these are all excited states. But excited states and ground states are all independent particles. 1440 half plus, since it is n I have put, so it is by definition half, and then another n. (1520), but this spin is 3 by 2 and parity minus, although isospin of course has to be half, and 1535 is also nucleon type, half minus now, spin is half, but parity, internal parity is minus, of course this is half. Then there are deltas, higher deltas. This delta has a mass of 1600, another delta mass 1620, and goes on. Many more particles are there, as I said, hundreds of particles exist. This is 3 half plus, this is half minus. Isospin of course has to be 3 by 2. Okay, these are all non-strange baryons, and strange baryons we call hyperons, right? That is the notation. Nomenclature I have already introduced, hyperons. And the lowest mass is lambda, which we have already discussed, and that is stable against strong interaction, it decays only by weak interaction. Lambda 1405, I am sorry, 1115 MeV, half plus. These we have discussed so many times, half plus. So, again JP I கொஞ்சம் பெருசாக்கியாச்சா?
கொஞ்சம் வாய்ஸ் கம்மியாக கேட்குதுன்னு சொல்கிறேன் சார், கொஞ்சம் லவுடாக
நான் லவுடாக பேசணுமா? கொஞ்சம் இது பண்ண முடியாதா, லவுடராக ஆக்க முடியாதா? அதை ஆம்ப்ளிஃபையரை கொஞ்சம். Are you able to hear me? Is everybody hearing me? They are able to hear, Kripa. They are able to hear. Only the letters have to be bigger, I mean magnified. So, some zoom is needed for that. Lambda, next is sigma, that is also stable against strong interaction, 1190. Remember JP again half, this is half plus, half plus. Isospin, this is 0 and this is 1. Then another sigma, which will of course come as a resonance, 1385. It is 3 half plus, isospin 1. Any strange baryon, any hyperon, which is strangeness, which is isospin 0 is called lambda, isospin 1 is called sigma, that is the notation. 1405 that is lambda. This is half minus intrinsic parity minus, and of course isospin 0 by definition. 1520. This again lambda, 3 half minus isospin 0, then 1660 sigma half plus isospin 1. So, these are all some examples I am giving. There are other hyperons with strangeness -2, you remember cascade. These are all strangeness -1, all of them. Of course, these are strangeness 0, non-strange I have already said. Hyperons, strangeness not equal to 0. Then there is a strangeness S is equal to 2 hyperon. They are called cascade. One cascade we already mentioned, 1520 mass, and Jp half plus and isospin half. And I am sorry, it is not 1520. That is the thing which is not a resonance. I mean, it is stable against strong interaction, and that is the 1320 which I already mentioned in the last hadronic table. Then this is the resonance particle 1530, again called cascade. Anything which is S is equal to S is modulus of S is equal to, okay, S is equal to -2 actually. Antiparticles cascade anti-cascades will have S is equal to +2. Okay, this is half plus, this is 3 half plus, and isospin half. That is the list of baryons, list of mesons now. There are some which are stable against strong interaction, which we have already discussed, like pi, k, and so on. But now I am going to include the resonances. So only some of them I am going to write here. This is the famous pion 140 MeV. This is the lightest hadron, remember 140, and that is what decides the range of the nuclear force to be 10 power minus 13 centimeter. As I indicated in my first lecture, the range is inversely actually h cross over mc, where m is the mass of the particle which is exchanged. By exchanging pion, you get a range of strong interaction of range 10 power minus 13 centimeter. That was Yukawa's prediction of pi, you remember that. And the range is really very big because the mass is very low, very big in the context of particle physics, but it is 10 power minus 13 centimeter, Jp and isospin. I am writing only the non-strange ones. Similarly, strange things k and its excited states, resonances can be written down, but I do not have it. You can look at the particle data booklet. Jp is 0 minus. Anything which is 0 is called scalar, but if its parity is minus, it is called pseudoscalar. So, pi is sometimes called a pseudoscalar particle. Spin is 1 because remember pi plus, pi minus, pi 0, 3 varieties are there. Then 550, this also I think I did mention last time, I do not remember now. 0 minus, isospin 0, it is a singlet. Then comes very important particles, the vector mesons. Vector means spin 1, Jp 1 minus, isospin 1 like pion. Then there is omega, again 780 mass, and Jp is 1 minus, and isospin 0. And there are many more. Phi, let me write down just one more. Phi 1020 MeV, 1 minus Jp, and isospin 0. Similarly, you can write down one more table. I do not have it here for some reason. So, it is a deluge, as I said. All these were discovered in the 50s, late 50s and the early 60s. was the time of the discovery of the resonance. Almost every day a new resonance was discovered by experimentalists. But it became too difficult for theorists to look at it. This zoo of particles, how to handle them, how to order them. And the symmetry SU3 was invented in that context in order to order these zoo of particles. So, let me go to that. SU3 is a generalization of SU2, which I already introduced last time. Heisenberg introduced it. As soon as he saw proton and neutron have similar properties, he said they are having isospin half. One is isospin plus half, another is isospin minus half. Exactly like spin plus half, spin direction plus half and minus half for electron, exactly like that. So, the SU2 symmetry is paralleling. Mathematically, it is the same as the theory of angular momentum, but physically, of course, it is very different. It is an internal space, not the physically observable, physically seen. Okay. So, is there any question on this? Otherwise, I will rub it off. I need now the full blackboard. Okay, shall I rub it off? If there is any question, you can ask me. As I already said, you can always shoot questions to me by email anytime, and I will try to answer them to the best of my ability. And my email address I already gave. In the SU2 context, SU2 of course was introduced by Heisenberg. It brought some order, namely instead of considering neutron and proton separately, it became collapsed into one particle. Instead of considering pi plus, pi minus, pi 0 as separate particles, they are components of one isomultiplet, isospin one object pi. So, like that the SU2 what we call isospin symmetry itself brought some order, but SU3 goes further, one step further, enlarges that symmetry. And in the context of SU2, there was a model called Fermi-Yang model. Fermi and Enrico Fermi and C.N. Yang constructed this model. They brought some further order using SU2. They said proton and neutron are elementary. All other hadrons are composites of proton, neutron and antiproton, antineutron. Pi, for instance, is a composite of, this is called nucleon and antinucleon. You can match all the quantum numbers. Similarly, all the particles here can be considered as composites of nucleon and antinucleon. So, there are only two elementary particles, even they get collapsed into one elementary particle. So, it was a great reduction of the hadrons. This is called the Fermi-Yang model. It is a composite model. We do not believe it now anymore, but I always go in the historical path, and this helped in generalizing it idea further. Sakata and his group in Japan generalized this after the strange. I discussed the discovery of strangeness quantum number last time. After the strangeness quantum number was discovered, all the strange particles cannot be obtained this way. So, to introduce one strange particle itself as an elementary particle. So, Sakata model considers proton, neutron and lambda as elementary, and everything else can be now composed from this. You can, this is a good exercise, try to balance the quantum numbers, isospin as well as strangeness by considering them as bound states of like this. All the mesons should be bound states of one of these as well as its antiparticle, as well as the antiparticle, whereas all the other baryons like sigma can be identified as a bound state of, in this model, how does sigma sigma will be a bound states of lambda and pi. Antiparticle sigma bar will be lambda bar and pi bar, like that. Because isospin can be balanced, isospin is 1 here, isospin 0 here, isospin 1 here, 1 plus 0 can give you 1, and like that. Cascade will be, let us try to compose cascade, that is 2 strange particles. I am going to have some difficulty here. So lambda, lambda, so strangeness minus 2 is obtained this way. Then baryon number has to be matched. Remember, all the baryons are baryon number 1. Cascade also has baryon number 1. Here baryon number is satisfied. That also we have to balance. Baryon number is an important counter number, I already mentioned. Without assigning baryon number to nucleon, we cannot understand why proton is stable. So baryon number 1 here, baryon number 0, baryon number 1. So baryon number 1 baryon number has to be removed. How do you do it? I think you simply put n bar, baryon number minus 1. So like that you can construct everything from Sakata model, just from this triplet of particles. Sakata model based on triplet. And so just as this doublet gives rise to SU2, this is a doublet, a symmetry between P and N gives SU2. That is the understanding of isospin symmetry of Heisenberg. Since now there is a triplet, so it leads to SU3. That is the birth of SU3. So SU3 was invented by Sakata in the context of his composite model of hadrons. But an Sakata model, I don't remember the dates, maybe late 1950s, after the strange particles were discovered, late 1950s. Fermi-Young was much earlier, I think, maybe 40s itself. No, not Young, maybe early 50s, this is late 50s, after strange particles were discovered in 54 or 55. Now, Gell-Mann, and especially Gell-Mann's name is going to come often, Gell-Mann and Neyman independently made an important observation. They agreed with SU3, but if you remember last time in the table, hadronic table, baryonic table which I gave last time, there was proton, neutron, lambda, sigma plus, sigma minus, sigma 0, cascade 0, and cascade minus. 8 of them. Gell-Mann and Neyman observed that it is sort of illogical to separate proton, neutron and lambda from these 8, because all the 8 particles behave alike in some sense. They all have spin parity half plus. So why separate P and lambda? So we should have a model. SU3 may be all right, but this should be assigned an octet representation of SU3. I will talk about what are the representations. Representations are the multiplets. For SU2, what are the representations? There is a twofold representation, that is I equal to half, threefold representation which is called isospin 1, and so on. So all integers are representation, but for SU3 all integers are not representation, but there are many integers, infinite number of them. So so they said we have to classify them as octet. So that was called the eightfold way. That was an important step in the development of hadronic physics. So let me now give some examples of representations of SU3 using I3 and Y. Remember Y, hypercharge, Y is nothing but baryon number plus strangeness. I introduced it in the second lecture. So I3Y plots. So let me give some of them. Now I require a lot of space and we have to draw some diagrams. I plot I3 horizontal axis and hypercharge along the vertical axis. So this is a pentagon, very symmetrical pentagon. What are these particles? This is neutron, proton. So, maybe I should have drawn it a little closer here. This is I 3 equal to plus half, I 3 equal to minus half, I 3 equal to minus 1, this is 0, I 3 equal to plus half, plus 1, plus 1, plus half, minus, this is 0 of course. And strangeness wise it is plus 1 here. So, this is plus 1 strangeness and this is minus 1. Remember nucleon is strangeness plus 1 because baryon number 1 strangeness 0. So, strangeness is 1 for that. So, now we can identify all the particles. This is sigma minus of course, and this will be sigma 0 as well as lambda. So, it is degenerate. So, I have to draw 2 circles first, sigma 0. Everywhere else there is only one particle, neutron, proton. Neutron has isospin I 3 minus half, p equal to plus half, and here of course I have to put I think cascade minus, cascade 0. We can count there are 8 of them. This is not a pentagon, this is an hexagon. So, 6 of them there and 2 of them here, so 8. So, this is the octet representation for baryon number 1 spin half plus. This is the way sometimes it is written, octet representation 8 there, and this is all of them are spin parity half plus. So, this is all of them now collapses essentially as different states of a single particle. So, 8 particles have been combined into a single particle. Similarly, for mesons, so this will be of course y equal to 1 and y equal to minus 1. Y equal to 1 is of course k, the k doublet, namely k plus and k 0 with isospin I 3 plus half minus half, of course this is 0, and here we have 1 and minus 1, and this is k equal to minus 1. This is anti k, so this has to be k minus has to be on the opposite corner, and this is k 0 bar. So, k stands for a doublet, and anti k again is a doublet. So, there are 4 k particles, remember. And here in the center somewhat similar to here, there is of course pi I have not written down at all. How come? This is minus 1. So, this is pi minus. Aperture 0, baryon number also is 0, strain is also 0. So, there has to be a pi 0 here, and this is pi plus. But then remember there was an eta, that is somewhat like the lambda there. So, again there is a degeneracy, pi 0 and eta. So, this can be called octet, but they are mesons 0 minus spin parity. So, these are 2 multiplets. Now, I am going to give you another very important multiplet. This is an inverted triangle. Y, and this is delta 1232 or 34 or whatever I wrote. This is delta. If you look at the Gelman-Nishijima formula, Q equal to I 3 plus baryon number plus strangeness divided by 2, which is what we call hypercharge. And if you put the baryon number, strangeness and I 3, you will see that first of all it has isospin 3 by 2. So, it is a quadruplet. there are 4 members. Iso spin plus 3 by 2 plus half, I mean I3 equal to plus 3 by 2 plus half, 0 minus half and minus 3 by 2. So this is actually plus 3 by 2, and then there will be delta plus 3 by 2 plus half delta minus so it should be delta 0. Iso spin charge gets displaced only by 1 unit, because when I3 changes by 1 unit and Q changes by only 1 unit, remember, delta 0 and delta minus. So when we say delta, it stands for these 4 particles. That symmetry was brought in by SU2 itself, but now we are going to have further symmetry. This becomes a component of this. This is what, remember, these are all resonances which I talked about today. This is the first resonance, and these other resonances I talked about today in the strange resonance table. Sigma 0. So this is isospin 1 object. And then cascade minus and cascade plus, cascade 0. And then finally omega minus. I mentioned this omega minus with strangeness minus 3, and so hypercharged minus 2 actually, omega minus. So y equal to plus 1 here, I think, because barrier number 1, and so this is hypercharge, barrier number 1 is strangeness 0, so hypercharge plus 1. This is hypercharge 0 because barrier number and strangeness cancel each other for sigma. This is hypercharge minus 1, and this is hypercharge minus 2. Strangeness minus 3, but hypercharge minus 2. Now what is this multiplied? This is, you can see, you count, there are 10 of them. 4 plus 3 plus 2 plus 1. So this is the decouplet or decimate. Decouplet, and spin parity is all the 10 particles collapse into just a single multiplets components of one object. That is what SU3, especially SU3 of Gell-Mann achieved eightfold way. SU3 is same as what Sakata had defined, but Gell-Mann and Neyman departed from it in a very important way. Now, not only that, this brought some regularity into the list of hadronic resonances, hadronic particles, resonances as well as stable particles. But then there is some more regularity, and remember the masses of this, this mass I already mentioned, I think 1670 MeV, this mass. If you look at the masses go on changing. This is 1520. And here also we know that nuclei 940, this is 1190, this is 1115, and this is 1320. Here also pi 140, and K and anti-K 490. So there are mass differences. I already mentioned even within SU2 multiplet, the masses are not the same. Proton and neutron have roughly 940 MeV. That 1 or 2 MeV mass difference is there between proton and neutron. Similarly, between charged pi and other pi, and that is because I will not mention it, but that is a very small mass, very small perturbation which changes it. But SU3, whatever causes SU3 symmetry is badly broken. It is a badly broken symmetry, but still it is very important for classification, as well as the way in which it is broken is very regular. That tells you many things about SU3 symmetry. You will see it when I finally construct the theory. Okay. SU3 is a broken symmetry, remember that. SU2 also, but SU3 especially. So not only you have to understand what is symmetry, but you have to understand what is broken symmetry. And in this SU3 context, again another Gell-Mann-Mokubo mass formula. Gelman actually discovered this formula, Mn nucleon mass plus M cascade divided by 2 equal to 1 over 4 into 3 m lambda plus m sigma. You just substitute the masses, you will see it is satisfied to a very good accuracy. This was what originally Gelman discovered, but then Okubo discovered that there is a more general formula, of which Gelman's formula is a particular case, and that is called Gelman-Okubo mass formula, and that says that within an SU3 multiplet, mass has to be parameters like this, some constant plus another constant times the hypercharge plus another constant times y squared by 4 minus I into I plus 1. When the isospin and hypercharge changes, the mass will change like this. That is what Okubo discovered, and so this whole thing is now called Gelman-Okubo mass formula. And from this, I give you a small exercise, derive this. That will give you a practice in handling all these quantum numbers correctly, okay, and that will help you to memorize this some of these quantum numbers. So this form, yeah. Yes, pardon me.
After that Gelman mass formula,
Yeah.
the board is not visible from the camera, so you can stop.
Oh, I thought they said up to this I can go.
Okay, now
Oh, you mean below? Below is not visible.
no. Earlier it was only visible.
Oh, I understand. So I have to stop the board up to this, is it only?
No, now they have rotated.
So is this visible?
Now it is not visible
Yeah.
till the left side.
Oh, this side is not visible, is it? This side is cut, huh?
Now everything is.
Now everything is okay. I think he has made some adjustment. Yeah. Now everything okay? So this is the for the octet. Derive this for the octet. Now for the decimate, there is more regularity. You can see that the isospin and hypercharge vary regularly. So there is a relationship between isospin and hypercharge. If you use that, you will see that m is equal to a plus one constant plus another constant times hypercharge. So this is for decimate, for tenfold representation. So you can see that the hypercharge changes linearly with mass. 1385 divided by 1232 is about 150, and 1520 minus, I am sorry, 1385 minus this is about 140 or 150. This minus this the same number, and this minus this also same number. So that is this equal spacing rule. It's called the equal spacing rule. I must mention one thing. When Gelman and Neyman proposed this, see, Neyman did it, but it was Gelman who went further. This particle had not been known at that time experimentally. On the basis of this equal spacing rule, Gelman said there has to be a single particle with strangeness -3 and hypercharge -2 with mass 1670, and that was discovered experimentally. So that was a prediction of Gelman. Experimentally verified in Brookhaven, I think, experimentally verified, I think around 1964. Exactly such a particle with precisely the same mass was discovered experimentally, and that established SU3. Therefore, established SU3 as a correct symmetry. Not only SU3, but SU3 in the eightfold way of representing it. This discovery experimentally established. Any question now? I want to rub off again. Now I want to go towards quark model, how quark model came up from SU3. That is the story I want to describe now. but in SU3 itself, if you have any questions, you can ask me. All right. You can always ask me later also. Now I can use the full blackboard, I hope. And are the letters visible now? Satya?
Yes.
Okay. I will make sure that letters are either this size or larger than this.
Since earlier they have zoomed it, no?
They have zoomed it, I think, yeah. Kripakaran
That is why only a part of the board was visible.
visible. So he has to go on shifting it, is it? Yeah, when it gets hidden, you tell me, I will, you can say it. I think Kripakaran can hear you also. He is in the other room, but he can hear you. Yeah.
Now maybe the left side of the board is zoomed. Thank you.
Up to this is visible, right? No, is good.
Now you have.
I see. He has to go on adjusting it. I can understand. Yeah. An important question now arises. The success of SU3 question. Remember, SU3 means it is a symmetry between 3 objects. SU2 is a symmetry between 2 objects. SU3 is a symmetry between 3 objects. That is why Sakata had proton, neutron, lambda. And SU3 is successful. So, what is the meaning of 3? What is 3 in SU3? This is the question. Gell-Mann did not want to face the question. I will explain the reason, come to the reasons. Here I want to mention an important historical event which took place, not many people know. I know it and I have recorded it in my review article, Bangalore event. You know, the last time I gave an archival, a reference to my, historical panorama. You look at that. In that, there is a small section called Bangalore event, connected with the Bangalore summer school in which Gell-Mann lectured on SU3. That is the first time he lectured on SU3. So there, Dalitz, my boss, my PhD boss, would be boss, he will become my boss later. He asked the question, what is the, why are you leaving out, see, in the, now proton and neutron lambda are part of the octet. So 3 is gone. So what is the meaning of your 3? He continued to ask the question, but Gell-Mann evaded it. And if Gell-Mann had answered it, Quarks would have been born in the Bangalore summer school. That is what I am saying here. And if any of us had answered it, we would have been the discoverers of quarks in this country. But we missed it. That is a missed opportunity, I call it. Answer is they are quarks. 3 of them, U, D, S. Gell-Mann did not answer it. The reason for Gell-Mann's reluctance may be twofold. Gell-Mann's reluctance to do this. This finally he did it only in 1964. By that time, and Bangalore event took place in 1961. By that time, Zweig also got onto the idea. So both Gell-Mann and Zweig are given the credit for quarks. But if he had done it in Bangalore, he would have got the full credit. 2 of them I will mention. One, the prevalence of asthmatics theory. Although I have been talking about the symmetries and I am going along the way which became finally successful. In 1961, around that time, if anybody visited particle physics scenario, they would have said asthmatics theory is the correct theory. In asthmatics theory, you don't think of any elementary particle or anything, all the particles are equal and all the hundreds or thousands of particles are equally elementary and one is the bound state of the other, composite. I think Satya asked that question. And it was called bootstrap. All the particles bootstrap with each other. The basic principles are the analytic S matrix. You extend the scattering amplitude into the complex plane, so a lot of complex variable theory went in. Dispersion relations played a very important role. Analyticity, maximal analyticity is called. The only properties which were used were analyticity of the S matrix in the complex energy plane and unitarity. These are the two important properties, and using this, people like G.F. Chu claimed that you can derive all the properties of hadrons. Ultimately, it did not work. The quark path became more successful, as we know now. And Gell-Mann also partly a believer of S matrix, but he did not believe in it completely, fortunately, because he himself invented quarks. But in his mind, S matrix played a role. So how can three of the particles, UDS, can be assigned an elementary role, primary role, out of which all other hadrons are formed? That is repugnant to the idea of S matrix theory. In S matrix theory, all particles are equal. It was called nuclear democracy principle. In fact, I remember in a lecture which the high priest of S matrix theory, G.F. Chu, delivered in Tata Institute. It was a public lecture. He claimed that he can prove, based on the principles of quantum mechanics and relativity, that no particle more elementary than proton and neutron can remain. That will contradict relativity and quantum mechanics, he claimed. But you see, all that has gone now. So Gell-Mann partly was a believer in it, so did not want to introduce an elementary particle, okay, like proton and UDS, which it took 3 years of courage in order to come out with that idea. Although you could have done it easily, any of us could have done it at that time. If we had if I had understood SU3 symmetry, I was still groping beginner in particle physics. But even Homi Bhabha was in the audience, M.G.K. Menon was in the audience, S.N. Bose, L.K. Pandit, Alladi Ramakrishnan, all of them were in the audience. But anyway, we all missed it. Second reason, this is my guess now. Quarks are fractionally charged. I will soon show why that is true. Fractionally charged. So far, all the elementary particles like electron and proton are integer multiples of charges. You take the electron charge or proton charge as the basic charge, all the particles are integer. Of course, delta plus has a doubly charge, all the nuclei are higher charges, but they are all integral multiples of one basic charge, which can be called the electronic charge. But quarks violate that, and no such fractionally charged particles had been seen experimentally. So because of these reasons, I think there was a reluctance to accept the idea of quarks. So let us now go to the properties of quarks. UDS, charge. For charge, we have to use Gell-Mann-Schema formula has to be valued anyway. I3 plus B plus S by 2. Let us first talk about the other quantum numbers. I3. I has to be plus. See, UD are doublets like proton and neutron, somewhat like proton and neutron. And I'm sorry, I is half for both of them, and I3 is plus half and minus half, and strangeness 0, 0, and this I equal to 0 here, I3 0, strangeness minus 1. Exactly like lambda as far as these properties are concerned. These are analogous to proton, neutron, lambda. Baryon number, what is baryon number? Now, you have introduced the 3 particles, and what is the connection of that to baryons? Baryons, remember, see, UDS are now supposed to be the elementary particles of which all other particles, baryons and mesons, are composed. Now, baryon is a quantum number, baryon number plus 1, and baryon has to be a composite of 3 quarks. If it cannot be one quark, because if it is one quark, then you are identifying, then it is Sakata model. So it has to be at least 3, because 2 cannot work, because these are all spin-half particles. The fundamental entities are always spin-half particles. With 2 spin-half particles, you cannot make spin-half. only spin 0 and spin 1 can be made. So it has to be 3 at least. So baryon number of quarks has to be 1/3. That is how the fractional charges come. And hypercharge also B plus S, so 1/3, 1/3 minus 2/3. So this is the table of quarks. And we can write down for U bar, you do it that for you. I mean you do it, U bar, D bar, S bar. So charge you can work out now, I am sorry, forgot. Use put it here, you will see this is plus 2/3, minus 1/3. Charges within an isomultiplet always differ by 1 unit, because I3 comes with a coefficient 1. S is equal to S also charge. So these are so they are all fractionally charged, and none of the fractionally charged particles had been seen. That is another reason why Gell-Mann did not like quarks in the beginning. So 1964, Gell-Mann had the courage to come out with quarks, and by that time another physicist, Zweig, although did it. That is the stage. And if you want to give the SU3 I3 Y I3 diagram, it is very simple, only 3 particles, Y I3 N P, and this is S. This is a triangular representation. Sorry, I3 here, Y here, minus half, plus half, and 0 here, hypercharge minus 1, hypercharge plus 1. So this is not the right way of doing it. The 0, so this is my hypercharge hypercharge. Yeah, it's not very important. In fact, I can give that as an exercise to you to draw. Draw the I3Y diagram. Or the quark triplet. It's a triplet now. Remember, that was the aim. We have to have the triplet to give meaning to SU3. So all of strong interactions therefore are invariant, and an SU3 symmetry, I am going to discuss SU3 symmetry in more detail. SU3 transformations, which are transformations which rotate these 3 quarks, 3, whereas SU2 analogously is a rotation in 2 dimensions. Okay. Any questions now? Let us go to a little bit more detail now, how the quark model functions. Quark model of the hadrons. So maybe we will do that tomorrow, I mean next lecture. Okay, I will leave it like this. I will construct all the hadrons from the quarks. So you can ask me questions now on what I have done so far, and then using these quarks, the hadrons, both baryons, strange as well as non-strange, and mesons have to be constructed. So the next lecture will be mostly that, and that leads to some problems, and how that problem was resolved, that's what I am going to describe. Yeah.
I have one question.
Yeah.
When spin was discovered,
Spin, ordinary spin.
it was discovered
Yeah,
which respond to the magnetic field.
correct.
So this isospin,
Hmm.
from this formula it is related to charge.
Hmm.
Is it like an intrinsic charge which responds to the electric field or something like that?
No, the electric charge is related to isospin in the Gelman-Schema formula, but there is no analogy to magnetic moment. You see, the ordinary spin of the electron or proton and neutron for that matter, they are all in physical space and they interact with electromagnetism, and then there is a magnetic moment connected with them. Isospin does not have any such connotation. There is no analogy to magnetic moment. And electromagnetism couples to the charge, you remember, and now we are saying that the charge can be decomposed in terms of some other quantum numbers like I3, baryon number, I3 and hypercharge, that's all. So charge is proportional to I3, it has a component coming from I3, but there is another thing which has nothing to do with the isospin. It is the same for all the members of a multiplet, and that is the hypercharge, which is B plus S. See, we are really doing this purely empirically based on observed facts. We still do not know why nature has this SU2 symmetry and SU3 symmetry. I will answer this question much later. You can ask the fundamental question. Actually, it will turn out that SU2 and SU3 are not fundamental symmetries. There are other symmetries which are more fundamental. They are the gauge symmetries which I talked about in my first lecture. And these turn out to be accidental symmetries. The baryon number, SU2, SU3, which played a very important role historically to go up to the standard model. But now we recognize they are accidental symmetries of the standard model Lagrangian. Remember, I wrote down the standard model Lagrangian on the first day. More or less, I will lead up to that, and at that point, you will see why this SU2 and SU3 came. Historically, they are very important. From a fundamental point of view, they are not that important. Still, we have to learn it because all the experimental data have to be correlated in terms of this SU2 and SU3. From the standard model point of view, these are accidental symmetries. That's what I want to mention. Even baryon number, which is so fundamental for our very existence, proton's existence depends on baryon number, turns out is an accidental symmetry of standard model. Standard model has other symmetries. Remember, I mentioned 12 symmetries, 12 kinds of charges. Standard model is based on those. But that standard model Lagrangian, which I wrote down, cannot have a baryon number violating interaction. And that is why a baryon number is considered. But if you go beyond standard model, like supersymmetry or grand unification, then baryon number is not conserved at all. That is why proton has to decay in many of these extensions of the standard model, especially grand unification. Supersymmetry also in principle will violate baryon number and so allow proton to decay, but they manage it by inventing another symmetry there called OR symmetry, which is in some sense artificial, but they had to do it. Okay?
Thank you.
Yeah. So we will have a break. My original idea was to start at 10:30, right?
11:30.
I'm sorry, 11:30. So please come back by 11:30.